Computers are in our offices, our homes, our pockets, our vehicles, and our buildings. They are everywhere. How can something so small that fits in the palm of my hand remember all my emails, photos, and music? And how can it do all the marvelous things it does so quickly and so easily? In this series, we will discover answers to all those questions and more. We're going to start with something simple, the light switch. You're no doubt familiar with it, as you would use it every day, unless you're a hermit and live in a cave. Light switches are pretty simple, really. Inside the light switch are two metal contacts. When the light switch is off, the contacts are held apart by a spring. When we turn on the light switch, electricity flows from the power supply, through the switch, through the light bulb, and back to the power supply, completing the circuit. If we turn the switch off again, the circuit is broken and no electricity can flow through the light bulb. The light goes out. Let's see that again. On, off. Inside a modern laptop computer, there are billions of switches. These switches are called transistors. Unlike the light switch, they are operated not by your hand, but by electricity. This transistor is off. No electricity can flow through it. By applying an electrical current, we can turn the transistor on. Electricity can flow through the transistor, just as it did when the light switch was on. Let's see that again. If we stop the electrical current, the transistor turns off. By applying electrical current, the transistor turns on, and once more electricity can flow through the transistor. In most cases, the thing controlling whether the transistor is on or off is another transistor. But we'll look at that again in a moment. Unlike a light switch, transistors can be made much smaller, and they have no moving parts. Transistors use the properties of the materials with which they are made to control the flow of electricity, rather than making a physical break in the circuit, as with the humble light switch. Transistors can be made really small. The iPhone has over 32 billion transistors. But how do we get a computer out of a pile of transistors? To build a simple computer, we need two things: a way to store or remember stuff, and a way to perform calculations and make decisions about this stuff. To begin with, we're going to look at the first of those two things: a way to store stuff in a computer. Binary is the system a computer uses to store and represent information using electricity. But what is binary anyway? You've probably heard of the decimal system. It's the system we humans use to read and write numbers. There are 10 digits in the decimal system, from 0 to 9. Distinguishing all these with electricity would be very difficult. Binary is a way of representing numbers using only two digits: 0 and 1. When the electricity is switched off, it corresponds to a 0. When the electricity is switched on, it corresponds to a 1. Let's take a look at an example now. We'll use chocolate chip cookies to illustrate. The number 13, written in the familiar decimal system. In primary school, we learned that each of the digits of a number can be placed in a column. In decimal, there are columns for ones, tens, 100s, 1000s, and so on. So the number 13 is composed of one lot of 10 and three lots of 1. Using cookies to illustrate, there is one lot of 10 cookies in the first column and three lots of 1 cookie in the second column, for a total of 13 cookies. Let's now look at the number 13 in binary. Just as in decimal, the binary system too has columns. The only difference is the columns have different values. In binary, we have a 1's column, a 2's column, a 4's column, and an 8's column. Each successive column has a value twice the previous. So the number 13 is composed of one lot of 8, one lot of 4, and one lot of 1. 1 times 8 plus 1 times 4 plus 1 times 1 equals 13. Using cookies again to illustrate, we have one lot of 8 cookies, one lot of 4 cookies, and one lot of 1 cookie. Again, a total of 13 cookies. So the binary system allows a number to be represented as a sequence of ones and zeros. Using electricity, we've learned that we can use the presence or absence of an electric current to indicate a 1 or a 0. We've seen that the number 13 can be written in binary as 1101. Correspondingly, we can represent the number 13 as a sequence of on or off signals on different wires in a circuit. You may have heard the term bit. A bit corresponds to a single 1 or 0 in a circuit. An average laptop in 2012 can store over 2 trillion bits. Of course, all these bits by themselves wouldn't be particularly useful. Imagine trying to figure out where one file starts and another finishes in a seemingly endless sea of bits. Fortunately, there is a simple solution. Early computer scientists began by grouping each successive group of 8 bits together and calling it a byte. A byte can store any whole number between 0 and 255. To store larger numbers or other types of information, the bytes are grouped to form larger and larger structures. Can you guess what a group of 4 bits is called? 4 bits is called a nibble, although the term doesn't get much use today. Computers use binary to store and represent numbers as a sequence of ones and zeros, or on and off electric signals. But what about music, email, websites, and photographs? By creating a special encoding for the type of information you want to represent, it is possible to store all these things using just binary numbers. Let's start with colours. The light you see coming from your computer screen is made up of 3 components: red, green, and blue. When all 3 colours are combined, they form white. By varying the intensity of each of the 3 components, an almost infinite number of colours can be achieved. And by using a single byte to represent the intensity of each component, red, green, and blue, it becomes possible to represent any colour electronically. For example, magenta, a bright shade of purple, is formed by mixing red and blue light at full intensity. The intensity of each of the components becomes a number between 0 and 255. We already know we can represent numbers using binary, so almost any colour can be represented using just 3 bytes, one for each component, red, green, and blue. In fact, the RGB, red, green, blue, colour space can represent over 16 million different colours and shades. We've looked at how to store numbers and colours in a computer. But what about text, emails, web pages, letters, and documents? You might think it would be much more difficult, but it is surprisingly just as easy, if not easier. Each letter and punctuation mark is assigned a unique number. For example, to represent the word hello, we look up each letter in the table and write the corresponding number. Starting with H, we have 72, E, 69, L, 76, in this case twice, and O, 79. Assigning each letter of the alphabet a unique numeric code allows us to convert any text to a sequence of numbers. and numbers, as we've already seen, can easily be represented in binary. The actual number used to represent a specific character depends on the encoding used by the programmer. Today, the most common encoding is called Unicode. In fact, by using Unicode, it's possible to represent text written in almost all the world's languages and writing systems. The Unicode standard has a specific number for over 110,000 different character representations, or glyphs. Let's recap. We've looked at how computers use binary to store and represent basic numeric information by encoding numbers as a series of ones and zeros, or on and off electronic signals. We've seen how these ones and zeros, or bits, can be grouped to form bytes, and how various schemes can be devised to store different types of information, including colours and text. Next time, we'll look at how computers perform calculations on and make decisions around this binary information.